So thanks everyone. So welcome to the SUSECON, to my session. Basically it's Guoqing and myself. So we have two presenters. So yeah. To start with this, so first of all, there are two terms, hopefully not misleading. The first one probably nowadays is very popular on storage. So this session is a storage, mostly is kind of traditional, slightly traditional. It's definitely not your open attics according to Ceph. So that's the first one. The second is high availability. So high availability has a lot of things, from the hardware to networking stack until the storage and to the application service. So this topic is mainly focused on so-called storage. Yes, exactly. So nice to have you to give more comments and right. So I think we have some conversation early days. Maybe we sometimes will check in touch with you and to how the things move to move along with this. Yeah. So along with that, I'm not sure how for the other audience, do you have some knowledge about availability primarily? Okay, you have. Okay, good. So okay. So I think to make it simple, I don't want to explore a lot of HA pacemaker related stuff, but basically this talk is primarily based on is powered by the pacemaker core sync stack. It's in the area to eliminate single point of failure in the storage related stuff. So to make it simple, one slide about HA is about to have the functional. Oops, is able to have this? Okay, so it's about to have a functional cluster. Once we have failure in one of the node and the whole cluster have with the help of pacemaker and the core sync and then migrate the failure node resource. This will be, as an example, will be the website will be moving into the other node of this cluster. So that's a concept, and the stack being managed by the pacemaker and the core sync. So that's so I think in this year's SUSECON we have quite several presentation around the availability. So my colleague Christopher, our HA architect, he did the session yesterday. So maybe some of you already joined that session. So I don't. Today we will not dive into too much into the HA stack itself. So it's about storage. It's a very basic element in our operating system. Is mostly block device, our very old hard disk, and the SATA, and now the VirtIO device, and also some of the volume group device, and quite many other device mapper device, and also MD RAID device. So still have many other things is not listed over here. So so that is the area in this presentation we try to cover a little bit. And the other basic element in the terms of the storage is about file system. So as an example, very easy to get is ext3, ext4. Now our SLE is default Butterfs, and also we have very famous, we support XFS for SLE. So those are the very very easy to get in our a standalone OS. To move along with that, you might be know OCFS2, you might be know GFS2. So those is cluster file system. We will slightly talk a little about a little bit today. So basically, our talk today can be very simple, just a block device and a file system. So in our focus, and also is about enterprise. There are two areas we're really keen about. It's about high available as an enterprise. So high available, we have a very typical scenario because of pacemaker. It's more in the way to introduce the approach is more to monitor the resource of the pacemaker and to fail over. Those kind of behavior is more in a way as a active passive. So very typical resource in pacemaker stack is about active passive behavior. In the meantime, in enterprise, we often have very high demand to looking for the active and active. So today we can dive some scenario about what's a situation about active. So other aspect is about an enterprise. We often looking into how to protect our data. So also some of the terms about the data replication, and also in a more critical situation, we'll have the data recovering. So we're starting from the small business. We have just a 2 PC, 2 blade, or even 2 VM. This is a very basic starting point. And then we're starting from the block device. So initially we just talking about the active and the passive situation. So thinking about we have 2 PC, 2 virtual machine. This is about the diagram. On the left is a machine. On the right side is another machine. So starting from this scenario is we don't have any physical shared storage. So since we are talking about the block device, and the title is about DRBD, which is a kernel feature, and right now is by the name is a data replication block device by network. So this is a on the diagram, each of the box in the green box, mostly I would say above the pacemaker and the coarsen layer, above are those you can think about those resource agent in pacemaker stack. So to have this DRBD being configured in the system, you will need to have several resource being configured in pacemaker, and to make it more To make it high available means we have one disk on one node, and then we have another disk in another node. In the terms of DRBD will be the master and the slave, and so basically here pacemaker and core sync is very important, is to manage the ordering dependency constraint of those different resource agents, and also the two disk is about to active and standby situation. So this is about DRBD. So in this stack in HA of SUSE, we have another block device. It can be high available, which is a HA-LVM. In the sense of pacemaker stack, it's very similar than the previous slides. So just a slightly different resource being used. So to make it high available, one of the things is so once we have failure on the host 1 to fail over to host 2, the shared storage right now is kind of shared, but by mirroring actually is by leveraging DRBD in this case. So only the difference is a resource is we need to stack a little bit different. And one of the things need to highlight for LVM in our latest SLE, we need to be careful to configure the LVM in proper way. For example, in SLE, we by default to have LVM method D is enabled since SLE-12. So that would be in a situation for host 1 and failover to host 2, this configuration will disable LVM method D to avoid a confusion of the system. So this is another high available block device in our product. Then we have another one, the third one, in terms of a high available solution can provide by the by our product is the iSCSI. So it's basically the similar. Right now in the diagram, we leverage DRBD to mirror the data of the host 1, and then when there are failure, we just fail over the corresponding iSCSI. I would say the iSCSI target into the other node, so make it available. Sometimes we might call as a iSCSI gateway or whatever. So the client can be available on the other node when host 1 failed. So this is basically the active passive approach so far.
Just a question on that.
Yep.
So when the initiator sees that the target goes away,
Right.
as long as the timeout is okay, is it likely to just wait? You know what I'm saying? With iSCSI, you can have the timeout and it'll wait for the portal to come back.
Okay, that's a good question. I think iSCSI doesn't persist in the session. So as long as the host 1, the target itself already died, being failed over to the other one, it cannot keep the session. So basically the session will need to reconnect, recover, go through the iSCSI process. Yeah.
I guess you have to configure the timeouts properly, and that should work as expected. Exactly if you're thinking about, I don't know, clvm or VMware high availability farm can connect the iSCSI unit, and you have to configure it on your virtual environment, on your hypervisor host. And if you configure the timeout properly,
it should just reconnect.
No, it's not interrupted. It's just to recover and
Yeah,
works just fine.
yeah, there is a recovery process by iSCSI protocol, I think.
Yeah,
right.
Like we already have like the Equalogic sound, and they do, like if one of the units goes down,
right.
the portal stays around, which is basically the same thing.
Right, right.
So as long as it comes back within your configured timeout,
right, right.
Then you should be highly available on the other side. So
yeah, yeah.
Thank you.
Another question. The iSCSI target or the iSCSI now, is it based on NIO or is it the traditional iSCSI?
In our SLE-12 is RL. Yep. So I think that's the block device level of SLE-12. So for SP2 can deliver such kind of scenario to your company. So now we move into the file system a little bit. So by using SLE and with our HA extension, we can build an HA-NAS, right? So we can have, for example, we can have NFS, and we can have NFS export resource agent. We have a file system underline, basically the same as a previous diagram. With the help of the resource agent, we can have the one system running the NFS port and failover to the other one. Again, I didn't modify the DRBD into the other topology. So along with this, we can easily apply the same approach to XFS and CFS Samba to help you to build a system can be available for Windows and Linux in the same time. So basically, this is very straightforward for this approach. So moving along with us to make the things is make the things is a little bit more appropriate for the company. We have more. We want more leverage some of our SAN device. Just for example, so basically, it's trying to share with you the diagram can be replaced DRBD with a real shared device. The shared device can be iSCSI, can be SAN device, and in this case, I also want to mention about to connect to the shared device, to connect to the SAN array. Normally, there will be involved another very important component of the multipass. So that is what we always recommend when we're using SAN device, for example, to help. That is part of a whole big HA stack. So that is good to mention over here. So in the previous, okay, yep.
I'm confused by why you use DRBD on the shift disk.
Oh, sorry. So I think there's something wrong. Okay, thank you to correcting this one. Yeah, this is definitely wrong. I think I should just remove that one. We should remove. Right. Yeah. I'm sorry. Yep. So yeah, previous diagram is more about 2 node, and definitely the company is growing, our storage is growing. So we have some motivation for the storage. So one of the aspects is we want to extend our storage. So scalability is one of the thoughts we always keep in the mind. We want to scale. And also the other motivation is the management. So we may have more expensive storage than our own PC. So we want the user to share the storage. And to do that, the cluster-aware component is now being involved into this conversation. And the same motivation will be the cost reason we want to share among the team, among the group, among the company. And also when more people using the same system, the performance always a demand to have the node to move from active passive into the active active situation. So to achieve this, so we are talking about sharing among the user for the same shared device. So in this case, basically it's just about the lock. So here we go. So we're still moving from the block device and then to the file system. On the block device level, previously we talked about the LVM. Now we are talking about the cluster LVM. So cluster LVM basically it's trying to enable multiple nodes to share LVM on the same shared disk. CLVM itself is a user space daemon who coordinate the LVM metadata. So, however, the purpose of LVM, CLVM is coordinated. The metadata itself doesn't coordinate and the real data of LVM. So, to interpret that, we can say if we have multiple nodes to share the same volume group, share the different volume group on a different node. By purpose, we have the dedicated volume on each of the different nodes. That is very safe, right? So by in the slides of later on, this will be pretty much useful to understand a very useful scenario. So again, for LVM itself, in this scenario, we need to be careful about the LVM metadata daemon of the system. So that has to be disabled. Otherwise, in the cluster, the LVM cache won't be synced very well. So that will create us a problem. Then moving from the clustered block device into cluster file system. So OCFS2 come into place. So OCFS2 itself is managed by the pacemaker stack, and which use the DRM and the bottom line as a lock mechanism to access the data of the same block device. So that will, because of the distributed log manager log, that helps. That is actually critical piece of the OCFS2 to leverage this mechanism to protect the data of this file system. So that means we can have multiple nodes to access the same file at the same time, but in theory, they are operate sequentially. And also, we can interpret it in a different way. Because of the lock, as long as we touch the same file, the performance will slow down. So as a recommendation will be to use OCFS2, we recommend to use a different file for performance reason. But if you just want to simplify the user, you don't care too much about performance, that's fine. You can use the same file simultaneously. So that's some way. That's the way of to let the user, let the administrator much more easier to play with the system. Then to add the both OCFS2 and the cluster LVM together, now we have a very interesting situation will be we can have both volume and also the data being coordinated well with the lock. So that is by cluster LVM, which provide the cluster volume group, which is allow us to resize the volume of this block device because of LVM. So that is safe for us to resize the volume. In the time, we can also leverage OCFS2 to resize the system as well. And in the meantime, we ensure the data among these two clusters are safe. So this will be a very typical scenario we could recommend. So until this stage, so we have roughly we have those typical scenario by using our SLE and plus HA extension to build a system. However, we still looking for one of the critical requirements in enterprise is about how the data is safe. So we have a few more slides, and Guoqing will help to talk about that.
Okay, I will talk a little about data replication, because it is important for customer to protect your data. Here we go. So we have some different concept of data replication. As you can see, the file level but we don't talk it. It's something in other concept than block level. And this is which I would like to talk about in next slides. And as you know, we just delivered SLE-12SP2. We add a new feature, classed MD read 1. So it means it just only support read 1 so far. And also self is really popular today. There's object storage replication. There's one section which also already covered in, I guess, yesterday. So let's back to the HA context. For HA, of course, the cluster, there are lots of nodes. Second, for performance, you need to have an active mode, not active passive. So the first thing is DRBD. DRBD, as the previous slide said, it's a distributed replication block device. So typically people think it is a network read 1. Each will allow you to create a mirror of 2 block device. But the 2 device is located in different sites, so it can work with a SUN. It is not suitable for a SUN, because it is copy data. When it write to the DRBD, one copy to local storage and another to remote by network. So it is not suitable for some case. But DRBD is, since it is network based, so it is recommended for GEO cluster storage. And DRBD now is the latest version is DRBD 9, and we upgrade our version from 8.4, I suppose is 8.4 to 9. Okay.
Question. Is DRBD 9 now the default in SLE-12, or is DRBD 8, I guess, supported for still available on SLE-12?
I guess it's 9.
Yeah.
9.
All right.
Thank you.
But there's a caveat. We only support 2.
Yeah.
Yeah.
And maybe one more subtle version is only science SP2, DRBD 9 is support. So SP1
Yeah, it's still
8.4.
8.4. So let's say another things about the data replication for HA. There's clvm, as Roger said before. For clvm, you can create different type of LV. For example, snapshot, stripped, and mirror D. So that's similar D provides the data replication for HA. I guess lots of people have used LVM before. But it is clvm is just extended from LVM, so there's no big difference. You can use this, basically the same command to handle clvm. For clvm, we create a mirrored LV to achieve data replication, and there's similar D, which used to track a mirror log info in a cluster. So we already have DRBD and the clvm similar D, but now we introduced a new feature, cluster MD, so far read 1 only. So it basically is built on top of traditional RAID, but it is class aware. Why we need class MD? The question is come from customer. We receive lots of complaints from customers. They say the clvm simulate D, the performance is not good. So class MD provides redundancy of RAID 1, which is mirror during the whole cluster. As I said, we just only support RAID 1, but we may consider to support other RAID level. The idea go to support maybe RAID 1.0, but not RAID 5, RAID 4, RAID 6, because the strip RAID is a little different. Okay.
What are the benefits when I use replicated and PUA instead of just a DRBD replication?
Yeah, for DRBD, you can to use it with a sum, because there is one storage in the list node and other storage in different node. But for class RAID, it could deal with sum. You can connect with different sum. And there's, I suppose, next, there is chart here, there's completion. Okay, there's some internal designs for class MD RAID 1. Class MD, it keeps the bitmap for each class node. During normal I/O access, it assumes cluster file system such as OCFS2, GFS2 will ensure will avoid the contention to the same block when it do I/O to class RAID 1, just same as clvm. With each node have its own bitmap, so it would no locking and no need to keep sync error during normal operation. So the performance is good compared is similar as native RAID. You can consider about. And so we have a bitmap for each node. The purpose of it is to perform when the class RAID needs sync and do recover, because it happens a lot for RAID. For also it's similar as clvm. It just only coordinates RAID 1 metadata. So the normal I/O is no need to coordinate. So that's why I said performance is close to native RAID 1. Why since the feature is motivated by the performance issue of clvm. So let's say why clvm have some limitation of performance. For clvm, it basically like a design flaw for clvm. It needs to send a message to use space, then broadcast to all the nodes in the cluster. Then acknowledgement need to back to the origin node, then send to the kernel space. If you look into the source code, you can find clvm is based on device mapper, and the MD RAID is based on MD. It is difficult. The kernel space code for MD is very, very complex, but for device mapper is pretty easy, simple. But in use space code is different. For use space tool, you may know LVM for device mapper things. and MD-LVM to handle MD. The logic is then different. LVM to have lots of code to handle logic things, but for MD-LVM, it's easy. So there's a total different. One is complex in kernel space, and other one is complex in user space. And I also add some links about class MD. The first one is in LWN, written by Neil Blanc. He is the previous maintainer of MD, and he involved with the design of class MD at the first beginning. And the second one is about how to use class read one, posted by Godwin. He's the first developer of this feature. Okay, so this is a competition about different technologies. So DRBD, as you can see, it supported active-active model, but only limited to 2 nodes. And but it's suitable for GR. I think Christopher also mentioned it yesterday. But it is not good for use it for a SUN environment. And in the second row, you can see clvm class MD. They are designed for basically the same scenario used for SUN. Not recommended for GR. But the performance is totally different. And also, both of them can support more than 2 nodes. But the node number is limited by pacemaker and the cosinker because it is the core layer of the whole cluster. So we did some tests with different things. There is a raw disk and clvm similar D. Oh, here. The first one is raw disk. The green one is traditional RAID, and the purple one is class MD, and the blue is similar. It is a little beyond my expectation. There's some case the class MD have a little good performance than traditional RAID, but I prefer both of them. Class MD is near to native RAID, and if you compare it with clvm, there's big difference here. This is tested with FIO tool, but with sync engine, with sync read write. There's different block size, 4K, 60K. For next one, we also test with async IO engine. And then you also can say clvm is very slow compared with class MD. So I would like to hand back to Roger.
Just to recap all those stuff, our / and plus HA extension, what is available as a building block. We can leverage all of those and combine and mix all together when it's required to make a high available storage. So that would be block level HA-DRBD, HA-LVM2, and the HA-iSCSI. And then coming to the shared situation, the shared active situation will be the cluster LVM2 and the cluster MD read 1. And the file system level will be with the active passive mode will be HA, FS, CFS, and also ext3, 4, and XFS. And also you can see the different the OCFS2, GFS2 is the cluster wide. So that's a whole our so far the HA extension can provide in HA scope. So that's all. So Any? Yeah.
Yeah, so for that question. Was the cluster D-Ray1 the code? Is it available upstream?
Yeah.
Yeah.
I think it's pretty stable now since 4.9. Welcome.
So in order to have the active file systems, it's got to be OCFS2 or GFS.
Yeah.
Yes. Yes.
Or it's just, you can't.
All right.
It's got to be a cluster file system.
Yeah.
Yes.
Sure.
Well, technically, of course, if you have a shared storage and you have things to forward it, nobody will stop you from mounting it from two sides. Trash. You need to have a file system that.
Yeah, no, I mean, that's the whole problem. It's great.
Yeah.
But as soon as the one guy goes to make a read and the other guy says, hey, or I mean, not the read, the other read, the write. But as soon as he finds it's not the same, it just, yeah.
Yeah. It's not good.
It's only worse.
Yeah. You want to test your backup or your tape libraries, then it would be a perfect idea.
So with this combination, we can use it.
Question
Okay.
about GFS2, is it included in Slash but not supported, or why is it in brackets?
We support GFS2, but by default we recommend the OCFS2.
So it's included and supported.
Yeah.
So any other question? Okay.
Okay.
Thank you very much.
Thank you. Thank you for coming.